Consider a universe. In this video, we are going to explain restricted comprehension axiom. So, if we take a universe, let's consider a green universe, and in this universe, let's say we've got these objects, sets. Now, some of these sets together as a collection form other sets, right? So let's say this yellow collection gives me that set, and let us say that this orange collection gives me that set. And let's say that these sets in here, they expand to certain sets. I'm going to use blue for that. And I'm going to use purple for this one. Now, as we know, not every collection is going to form a set. For example, in this universe that we've displayed so far, this collection, the collection consisting of just this set, does not form a set. Well, in principle, we don't know what the elements of this object here are because it hasn't been expanded. Also, we don't know what the elements of that object are. With the given information here, because the elements haven't been indicated, if we claim that this is a concrete example of a universe, then we could assume that without indicating the elements, what we have in mind is that these sets do not have any elements. So if they do not, if both this one and that one, and also these two, by the way, and these ones as well, if they're all empty sets, then we can be sure that this collection does not form a set. The number of collections in general would be 2 to the power n, where n is the number of objects in the universe. And of course, 2 to the power n is always greater than n. So at least with finite universes, it is impossible for every collection to form a set simply because there are so much more collections than there are sets. Right? And of course, the Russell's paradox tells us that even in arbitrary universes that are not necessarily finite, we can always find a collection that does not form a set. So not every collection forms a set. But in set theory, we want there to be as many sets as possible. And so the axioms of set theory will stipulate that certain types of sets exist, or in other words, certain types of collections form sets. Now, the axiom of restricted comprehension tells us that if a certain collection forms a set, then its sub-collection must also form a set. But this must be a sub-collection defined by a certain formula. So for example, the yellow collection here forms a set. And let's now expand this element here. Let's say this one is indeed an empty set. There we go. So consider now the formula. I will need some space now here. And I'm going to design a formula which will be used for me to select a certain sub-collection of the yellow collection. So let's say the formula says, so it should be a formula about a set. Let's use the letter X to refer to that set. And so the formula should say something about X. And let's say the formula says there exists A such that A is an element of X. So basically the formula says that the set has an element. In other words, it says that it's not an empty set. Great. So now let's look at this universe and let's see which sets in this universe satisfy the formula. And particularly, we're interested in those sets in the universe that satisfy the formula and are at the same time members of this collection. This collection does form a set. It's the set, let's call it A, or maybe a better name for this one would be capital X. And now if we start examining the sets in this universe, we can't really say about these three because we don't know what their elements are unless the information displayed here is complete, and then we can assume they are all empty sets, in which case they don't satisfy the formula. But let's say they're not all empty sets. For example, let's say this one does have certain elements, then definitely it will satisfy the formula. I'm actually duplicating some of the colors, so now the colors no longer are uniquely assigned to sets. So if this is so, then this object here, this set here, would be one of the x's satisfying the formula. But we're not interested in that. We're only interested in those ones that fall in a certain collection, and for us now we picked the yellow collection for that. And so we want to select those small x's satisfying the formula from the collection, not from outside the collection. Now inside the collection, if we start examining which x's satisfy this formula, we see that this set over here does not satisfy the formula because it's the empty set, and the formula says that X must contain an element. On the other hand, these two both have an element, and therefore both of them satisfy the formula. So the collection formed, the sub-collection of the yellow collection formed by this formula is this one. And we're going to color in that with red. In notation, this collection can be written out like this. So we use this symbol for notating collections and sets, and now we say we want all possible x's, not just arbitrary x's, but those that are elements of our chosen set X. In other words, those that belong to the yellow collection, such that they satisfy the formula. So in other words, such that this holds. There exists A being an element of X. Now, that thing here, this thing here refers to the red collection. And what restricted comprehension says is that the red collection must also form a set. So there must be a set in the universe whose elements are exactly those things which fall in the red collection. And let's assume this is that set, so that we try to validate the restricted comprehension, at least in the instance of this specific choice of X and the formula. So we can call this thing Y. And so we can now write down that this collection is actually can also be viewed as a set, and as a set, it is the set Y. Okay, so to to explain that, to summarize and re-explain that, so what does restricted comprehension say? It says that given a collection which forms a set, so in other words, given a set X, if we pick out from that set certain elements satisfying a certain formula, so certain X is satisfying a certain formula, then that collection will also form a set. In other words, there will exist a set, in this case it's Y, whose elements are exactly those small x's that satisfy the formula.